We present SpaceTimePilot, the first video diffusion model that disentangles space and time for controllable generative rendering. Given a single input video, SpaceTimePilot enables free and independent control over both camera viewpoint and temporal motion, supporting bullet time, slow motion, reverse playback, and arbitrary space-time trajectories within one unified model. Previous camera control methods, such as Recam Master, allow flexible camera motion in dynamic scenes but keep time strictly monotonic, preventing truly 4D exploration. Meanwhile, multi-view 4D diffusion models, such as CAT 4D, generate only discrete images instead of continuous video sequences. In contrast, SpaceTimePilot synthesizes continuous, arbitrary space-time trajectories for dynamic scenes by disentangling spatial and temporal control. While enabling dual control in diffusion models is well known, the primary obstacle remains the lack of appropriate training datasets. To overcome this, we propose a simple yet effective temporal warping training scheme that mimics the temporal variations of a target view. Specifically, given a pair of multi-view videos of a scene, we keep the source video intact while augmenting the target video with several temporal warping patterns, such as reverse motion, slow motion, and zigzag motion. This creates variations in the time sequence without breaking the temporal continuity of the video model. We also added freezing temporal augmentations, where frames are essentially repeated to mimic the bullet time effect in the target video. During training, the diffusion process is conditioned on both the camera trajectory and the temporal trajectory. Training with temporal warping augmentation directly leads to the model learning to disentangle space and time effectively. Meanwhile, to achieve much sharper results, especially for bullet time, we introduce a synthetic dataset called CamXTime. This is the first video dataset to provide a full grid rendering across all space and time dimensions. Training on both these enhanced augmentations and our new dataset leads to much sharper temporal control. Moreover, to unlock the limits of generating only 81 frames, we trained a simple multi-turn model where two videos are used as conditions. We can iteratively provide different temporal and camera trajectories, allowing the model to connect them seamlessly. With this, we can achieve effects such as large-scale viewpoint changes by splitting the task into multiple sections, where each section handles only part of the temporal range. Thanks for watching.